The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi, my name is Pramukhangaran. I'm supposed to be one of the four, but it remains that I am the only one now. My project was about global illumination, and it's about rendering 3D scenes. So first, let me tell you about the direct illumination model. This is something you can achieve with ray tracing. As you can see, the image above is rendered by shooting a ray from your eyes and then taking the local lighting properties of the materials and then see whether there's a light coming to that point or not and then figure out the color. So in this model, there's a lot of things unnatural about this because as you can see, the light is an area light, but then the shadow is like very solid shadow as if it's lit by a point light and something like that. And you can see that the ceiling is not lit at all. This means that this model of lighting doesn't take into account the light that bounces between the walls and lighting parts that should have been lit in the real, in the real life scene. As you can see. So global illumination basically tries to fix that. And the effects you can achieve with global illumination algorithms are basically soft shadows. Color bleeding, you can see that there's a very pale shade of blue here. And caustics, which means that light from here goes through the glasses and then focus on here. So at first, when I started the project, I want to globally illuminate a very simple scene, which is the Cornell box. It's just basically this box with, and you replace these two spheres with two white boxes. And then you can observe color bleeding and something like that. And I want to do it in real time with caustics. However, the things I accomplish are, well, I globally illuminate the Cornell box as I promised. In real time, no, it's too slow. With caustic, didn't implement photon mapping, but and sadly, there's still a lot of room for optimization. So kind of disappointed in myself a little bit, but yeah, that's life. So the algorithm I use for global illumination is called instant radiosity. It's by some German guy called Alexander Keller. It's good for scene with diffuse objects, which means that scenes that doesn't have objects that reflects light or let light transmit through. Diffuse objects can be just this table and something like that. Basically, it means that when light strikes it, it just bounces off randomly. As such, it can do caustics, although it is very simple to implement once you have the core. So let me describe the algorithm. You start with the light source, and then you emit artificial light particles and let them bounce around the scene. And then you will have some more light source, and then you ray trace using those light source in the scene, basically. So this is the illustration of the algorithm. First, you have the light which goes off from this square light, and then you illuminate the scene with it, and then you bounce some lights off, and then illuminate the scene, and then you combine the results, basically. So in my implementation, I just have, at the beginning, I have one SPU scatter all the light particles. The number of light particles I scatter is about 128. And as they bounce around, it ends up to be about 250 light sources in total. And then I render the scene by splitting the scene into horizontal slabs, and then just give the slabs to each SPU to render. In this way, since the scene is very small, it can just preload them to every SPU, and they all can work independently. So there's minimal communication going around. And since I didn't implement any other smart data structure to take care of the geometry, I just used brute force ray tracing. My scenes have only 8 objects anyway.
Maybe it might be a good point to see if there's a question at that.
Wait. So the SPUs are doing rendering or ray tracing? Or
Ray tracing, yes, basically.
But I mean, can a ray move from one slab to another depending on a reflection or something?
No. Basically, if you trace the light there, the SPU have all the description of the scene, so it can trace the ray throughout the scene. But it's responsible for only the pixels in the slabs.
Okay.
The complexity is kind of bad because all the times the time is you have your image size, the number of pixels, times the number of light particles, which is about 200. And then since I use brute force ray shooting, you have to times by the size of objects. But at first I thought I have only 8 objects anyway, so it's not going to be a big performance drag. But then I came to a realization that this algorithm initially was conceived for using with programmable graphics hardware, which can do really dumb tasks like taking a point light source and illuminate a scene with shadows very fast. So it turns out that this algorithm is not really suited for the cell, basically. I wish I could have done better on this. This 500 by 12 times 512 scene took 20 seconds to render on the cell, but the original paper, they render something bigger, a little bigger than this in 24 seconds with GPU, basically, so it's kind of disappointing. Hello?
24 seconds on what type of a machine? Can you hear me?
Yes, but not very clearly.
24 seconds on what kind of a machine?
Original paper took 24 seconds.
24 seconds on a 75 megahertz something machine with a GPU.
Okay. And did you try without using any SPU, just using CPU?
Just using the CPU and the GPU and that one.
The question was, did you try using...
You are saying if you just use CPU without any parallel inter, how much time does it take?
Oh, times that by 6. Basically, however, the speed up is proportional to the number of processors used. I basically graphed the runtime with the number of processors. This is in log scale, so as you can see, so that's the best you can do about parallelism there, basically. Yes?
So runtime is normalized to just the PPU?
Using the SPU.
So what are the units for the y-axis?
The y-axis is runtime in seconds.
I see. So 3.7 seconds, 3.6
Yes.
seconds for one SPU.
Yes. 3.6 seconds per one SPU. And as you increase, the times go down. You just divide that by that. Is that clear?
They're all using the PPU as well?
No, the PPU doesn't do anything. Just use
So didn't you say 20 seconds on your previous slide?
This is different image size. Yes.
Oh, okay. Different.
Sorry,
different
I
scene
didn't make
size?
that clear.
Sure. Okay.
And this is 128, so it's about 16 times faster. I couldn't wait for like.
Sure.
So here are some images I rendered. There are 8 objects in here, and it took like 20.5 seconds with 6 SPUs. Another image that I rendered is a miniature of a cornell box. It took 20.2 seconds in 6 SPU.
So why is the ceiling still solid black?
Yes, I don't know that as well. Maybe it's a bug. Maybe it's about the distribution of the particle light source. Probably, I think when it goes to the wall or to the floor, it's get severely attenuated that it cannot really lit the ceiling, basically. Also, there's a comparison between my rendering and the real coordinate box. Basically, yes, there's still a lot of bugs around. Basically, the ceiling is not lit, and it's kind of strange that I see some red tinges here instead of green as in this one. So probably I have to fix that as well. But as you can see, we have a soft shadows and then some color bleeding.
How do you determine the location of the light sources?
How do I determine the?
Are you?
Are you giving this input to the algorithm the location of the light source?
Yes, basically.
And they can be arbitrary positions within the box, or?
Yes, basically. This one is just a square object, which is written in the scene description file, and I can locate them wherever I want, basically. The light particles goes down from here. So there is something that can be further optimized. Basically, if I had decided to use accelerated data structure, the complexity of that image size times objects times number of light sources, this term will be reduced to log, and probably you see about 3x speed up.
Can you give an example of accelerated instructions?
Basically, there are some, the most popular one is probably the, what is it called? It's, for example, the KD tree, for example. Actually, I learned in class that basically you can achieve about 2 or 3x speed up by rearranging the data so that you can trace 4 rays or 16 rays at a time instead of doing one at a time in the approach I'm taking. And if you do that, it's faster. There's also, in the program, I have a lot of objects, and each of them has a transform associated to them so that I can locate them wherever I want, and the object can be anything. But there's another approach which says I just take anything to be a collection of triangles. And if you have triangles, the description is just 3 points in space, and you don't need transform to do location and something like that. And basically, checking whether a ray hits a triangle or not will be faster. So thank you very much.
Do you know the work that was done here by Julie Dorsey in illumination?
I have no idea.
She basically used the trick of pre-computing, doing the ray tracing for some fixed number of source locations, and then just rendering in real time by taking a linear superposition of these ray traced images. So long as you could approximate your light source by a linear combination of some fixed repertoire of light sources, you didn't think about taking that shortcut, presumably.
I did think about that shortcut, basically. Should I give a demo or something like that, since I have 2 minutes left? Let's see. So basically, there's this output.gga, which I'm going to remove because I'm going to generate it. The scene I'm going to render is going to be a Cornell box with a cube and a sphere in it. Yes?
How easily could you change the light source?
I can just move the object into light source.
Okay, can you do that with the...
Sure. Let's change it to a point light source then. So right now the current light source is this square. I'm going to comment it out. And change it to the point light source here. And then there we go. That's too quick, but basically, there's a point light source located around here. So the scene is lit with one point light, so as to expected, the shadows are. Sorry.
Well, we should probably say one more question?
One more question.
Sure.
So just dividing the scene equally seems it would get good load balancing if you had like roughly equal complexity across different sections.
Yes.
If you have a really complex object, or if you have like reflections that go much deeper some places than others, couldn't an equal division lead to bad load balancing? I mean, did you think about other divisions?
I suppose, but basically other approach that I think of, which basically probably can divide the scene in a really fine-grained manner.
Oh, you just do like a striping then?
Yes.
Yeah. Okay. So is there a reason that you chose blocks?
The communication, how hard was to get the communication working? So what do you communicate and how often do you communicate?
Professor Suman asked how much is to communicate, how often do the SPU communicate with one another, right? And the PPU, and how often do I do that?
Yes.
Basically, before the SPU start running, the PPU send it the scene description, and then it sends it the task that say, I want you to render this pixel to this pixel, and that's it. And then the SPU just streams the pixels to the main memory.
Okay, so what you do is you do a static balance, static distribution of work around.
Yes.
And then when you're done, everybody send it back and then you synchronize.
Yes.
Okay.
Basically.